Right, this is June 15 AQA C3 paper. Again, pause it as you have to, don't do it, let it play on, make the most of it. So I'll have a go and we'll see what we get to. So by writing that, use the quotient rule to differentiate it. So you want to differentiate, so if y equals sine x over cos x, you're going to want to use the quotient rule. Now, quotient rule, I think, is in the formula book, but it is, if it's u over v, then it's the bottom term times the differential of the top minus the top term times the differential of the bottom all over the bottom one squared. So v du minus, and the quotient is minus, the product is always plus. So the quotient is minus over the bottom one squared. So I'm going to do it as I've just said. So the bottom term times the differential of the top, so sine goes to cos, minus the top term, which is sine x, times the differential of the bottom, so cos goes to minus sine, all over the bottom one squared. So you've got cos squared x plus, because you're minus and the minus, sine squared x over, cos squared x. So cos squared plus sine squared from your C2 equals 1. Looking at where you want to go to, 1 over cos squared is actually sec squared. But because they've given you the answer, you needed to have that. Okay, but you also needed to write the answer that was given. Don't just stop. Okay, so that's good. So we know that that's true. So we've differentiated tan, we know we get sec squared. So that's good. So when you integrate sec squared, you would get tan, would be the hint that I think they're trying to give you. So let's clear that and have a look at B. So we're now going to integrate. So we're integrating x sec squared x. So there are two terms in terms of x, which means we're going to use the equivalent of the product rule for integration, which is integration by parts. So if I write the formula up here in white, if you're given to integrate two things, they call them u and then dv by dx, you'll end up with uv minus the integral of v du by dx in terms of dx. So your initial terms aren't u and v, they are u and dv by dx. So if I'm looking here, and remember when you're integrating like this, we would always look for late. So this is what the u is. So if it was a u, would be a log. If there were logs, u is algebra. If there's algebra, u is trig. If there's only trig, and then u is exponential is the last one. So here, there's only algebra. So u is, well, no, there's algebra and trig. So u is x, and the other term, which is the dv by dx, is sec squared x. Right, so I'm going to differentiate u to get 1, which is lovely, and I'm going to integrate sec squared, which strangely enough we've just proved is tan x. So that's wonderful. Okay, so now let's try and shove it into that hideous looking formula. So I've got u dv by dx integrated will give me u times v, so u is x, times v, which is tan x, brilliant, minus the integral of v, which is tan x, times du by dx, which is 1 with respect to x. So I've got x tan x minus the integral of tan x. Now, if in doubt, then you should look at the formula book. And the formula book has on a page, if I can find it. So that formula is on page 8 at the bottom of all that. And then further up there, integration of tan x is ln sec x. So here you would write minus ln sec x. And because you're integrating, you have the integration constant. Okay, so that is brilliant. And I am going to write that here. So equals x tan x minus ln sec x plus c. Okay, so now we are looking to region bound by this. So we're going to look at the volume. Okay, so if we go back to basics, we're looking at volume around the x-axis. We may have a curve. We don't know what this curve looks like. I don't know what it looks like. And we're thinking about doing round this curve, okay, to get a volume. So we're going to shove this thing round, and with respect to x, round the x-axis. So these are lots of circles, and we want to sum up all the circles. So that's what integration means. We're going to sum between specific values all the areas of the circles, and the total area of all those circles, infinitely small across this side, will give us the volume. So pi r squared is the area of a circle. Pi can come out, it's just a number. We're going to integrate between a and b, whatever a and b is. Our radius of this circle is actually, at this point x, it's just the y value. So that's why it ends up as pi y squared dx to find the volume of revolution of a shape. So, looking at that, the first thing we've got to do is go back and see what our y is. Now our y here is 5 root x in a bracket sec x. There's no pluses, so when you square it, you're going to square each and every single dit. So you're going to end up with 25x sec squared x. So each term is squared because there's no plus. It's not like you've got two different brackets. It's just you're squaring every single term. So brilliant. So now, because that's y squared, we're going to do pi y squared. But 25 is just a number as well, so I'm going to stick that out the front and then end up with x sec squared x. Now hopefully at this point you should have bells ringing loudly in your head saying, oh, I recognise that. Haven't I just done that? Oh my goodness, yes you have. So we're going to put x tan x here, because that is what the integral of you've done. Sec x. And we won't need the plus c this time, and we only want to do it between 0 and 1. 0 and 1. Fantastic. So you have 25 pi times 1 tan of 1. A bit weird, minus ln of sec 1. Okay, I need a really big funny bracket here. Take away 0 times tan of 0 minus ln of sec of 0, with a funny little bracket there. Good. Okay, so what you should end up with is something really horrid, but ending up with rounded to two significant figures, as you have been asked, 74. Isn't that fantastic? So shoving that into your calculator and getting the final answer is, this final answer down here is 1 mark. Getting to this point is 1 mark. If you think it's going to take you more than a minute to get that 74, and you prefer to spend a minute on trying to get some other marks, please do. But this was only 3 marks, this last bit. This bit was 1, this bit was another, and that was the last bit. So you decide. But that's question 5 done.